Hi everyone, so we're going to pick up with our discussion on special relativity. We're going to focus on length contraction. The idea that not only is how you measure time relative to your frame of reference, but also how you measure distance. And then I'd like to finish with a problem where we look at how both can be solved from different frames of references. So as I mentioned in the first bullet, since the speed of light is constant in all frames and therefore time intervals are relative in different frames, it would stand that length intervals are also relative. So we're going to look at and derive an equation for how you measure length in two different frames of reference. And there's going to be a proper length and a L prime, just like we had for time. So we have we have a situation. We're going to have a spaceship fly from Earth to a nearby star, Alpha Centauri. And we're looking at it from two different frames. The first frame is from the Earth. In other words, you are an observer, an astronomer on Earth looking at this spaceship fly to Alpha Centauri. And the second frame, this one, B, is if you're in the spaceship itself. So we already know that how much time we measure for the spaceship to travel from here to here is going to be different than what they measure. They will measure a short time compared to this time, and so we also want to look at what the length is. In fact, if you look closely at the diagram, it's kind of telling you how we measure length from the Earth is going to be longer than the length that people on a spaceship seem to measure. In other words, they're going to think Alpha Centauri, the distance between Earth and Alpha Centauri, is less than what we measure. But let's understand how that arises. Okay, so let's start with relative to the Earth, which I already said is figure A. So the key thing is, in this frame of reference, the object in question, the distance in question, again, let me make clear, is from the Earth to Alpha Centauri. So if we're looking for that distance, since Alpha Centauri is rest relative to us, we call it the proper distance. That's the L naught. Okay, so that's important. In the spaceship, the proper time is in here because the spaceship doesn't seem to be moving. The clock doesn't seem moving. When we're talking about length, we measure proper length between the two distances where those objects do not seem to be moving. So since Alpha Centauri is not moving relative to the Earth, that's a proper length. If you're in a spaceship, Alpha Centauri does seem to be moving, so that's not the proper length. And that's what we want to come up with an equation for, is what length they measured. So the time it takes to go from Earth to that is going to be T prime. Okay, so this is where you got to be real careful about differentiating between T prime, T naught, L prime, and L naught. Okay, so this is T prime because the spaceship is moving relative to us. The clock is on the spaceship, so that's why it's T prime. But that's going to be L naught, the distance as measured by us, which is the proper length, divided by how fast the spaceship is going, which is V. Okay, well, that's a simple equation. It's not immediately obvious that the time would be T prime and the length would be the proper time. Okay, so review that, and if you have questions, you can always ask. So now what we want to do is relate this to this length here, and we're going to use the distinction between T prime and the proper time to make that connection. So we already know from the previous equation that T naught, or the proper time, is equal to the T prime divided by the gamma, the Lorentz factor. Okay, so review that on the other side, because we had it solved for T prime as T naught times gamma. So it would follow then that if T prime is L naught over V, and I substitute it into here, then I'm going to get that the proper time is the proper length divided by gamma times the velocity of the spaceship. And if I cross multiply, I got T naught times V is simply equal to the proper length divided by the gamma factor. And if you look at that, that's a velocity times a time. That's the L we're looking for, okay, up here. So we can say the L as measured by the spaceship, the distance it traveled from Earth to Alpha Centauri, is equal to the distance we see between Earth and Alpha Centauri divided by the gamma factor, which is based on how fast the craft is moving. In other words, the distance L is measured in the spaceship, and what we want to see is contracted. Let me back up a second. We saw that in the diagram, but if we look at this equation, since we know gamma is always greater than 1, then the proper length divided by that is going to give us a value always less than 1. So that's another key outcome of special relativity, is if you are in, well, how can I put this? So if something is moving, okay, the distance you seem to travel is always going to be less than what someone else measures standing outside of it, okay? Or the length that you measure is contracted. Space is contracted. You don't know that as you're moving because you don't think you're moving. But when you work out all the calculations, it will give us consistent answers for both frames of reference, and that's important. Okay, so let's do a quick problem. So let's say we know Alpha Centauri is a certain distance away from Earth. Let's just label that now. That's the proper length. Again, because Alpha Centauri is not moving relative to us. A rocket travels from Earth to Centauri at 99% the speed of light. That's pretty ambitious, but I want to do a different speed than the muon problem. How long does the journey take as measured by an experimenter on Earth? And then we're going to basically do the same question for if you're in the rocket. So in order to do this, I'm asking for a time. We want to ask ourselves, is this t naught or t prime? So pause this and answer it for yourself. All right. Okay, I think I already mentioned it earlier, but reiterate, this is going to be t prime because the clock in question, the time on a rocket, it's moving relative to us, so we want to do that. So as we saw before, t prime, we're not going to use the gamma function yet because we don't know what the proper time is. We're going to just use the distance divided by velocity. So if we plug in the numbers, I trust you can do that. I'll just put in 4 times 10 to the 16th. Okay. Now, in this case, I do need the actual speed of light in meters per second. I can't just use a fraction of c. It's 0.99 c, which is essentially 3 times 10 to the 8th, right? The 0.99 is going to have very little effect, but I'll put it in there anyway. And when I do that, I get 1.3 times 10 to the 8th seconds. Okay? Now, let me convert that to years for you. That's about 4.2 years. And that's, in other words, that star is 4 light years away. So what's measured by the astronaut on the rocket? Okay? Knows how much time from the astronaut's frame does it take? Well, to do that, we're basically going to essentially use t naught. That's the proper time because on the rocket, your clock doesn't seem to be moving. Is simply t prime divided by the gamma factor. Okay? So let's do gamma right over here. So gamma, by definition, right, is equal to 1 over 1 minus v squared over c squared, and the square root of all that. So when I plug in the numbers, and I suggest you do that, because we're going 99% the speed of light, gamma is going to be relatively high, but it's surprisingly not as high as you might think. It's essentially 7. So my t naught is going to be, I'm going to do this in years now, but you could do it in seconds. 4.2 years divided by 7, which is 0.67 years. So whereas we saw the astronauts aged by 4.2 years because it took them 4.2 years to get to Alpha Centauri, they will only be 0.67 years older. That's crazy. So that's 2/3 of a year. That's what, 8 months, I think. So if there were twins on Earth and one of the twins stayed home and the other one was in a rocket, they would be different now by about 3.5 years. And that's pretty cool. Now there's a paradox that arises from that, which will be addressed through some minute physics ones. Next, what distance to Alpha Centauri does the astronomer measure? So is this L or L naught? Well, if the distance measured by the experiment on Earth was L naught, it would stand to reason that the traveler in the spaceship is going to measure L. So we can, since we know gamma, we can use the equation, the length and contraction equation, which is equal to L naught all over gamma. So this is 4 times 10 to the 16th divided by 7. So this is a fairly trivial calculation. But the point is it contracts by a factor of 7. So another way we could look at that is instead of meters, which is perfectly valid, if this was 4.72 years away, then it's 0.67 light years away. Okay. So that's our calculations for special relativity. I'm going to finish with, and I will have to leave links for you because I don't want to play these right here. There are some really interesting ways, other ways of looking at that. So I'm going to put 4 links here, watch them, try to make sense of them, enjoy them, especially the twin paradox one, because that's an interesting one. Let me just set up the twin paradox for you. Okay, and it's not so much that the twins age at different rates, it's the question of which one ages at different rates. Because in this problem we said, all right, this person is moving relative to us, so they're going to age more slowly. But from their frame, they're never moving. So if they go to Alpha Centauri and back, it's the Earth moved away from them, and then the Earth that came back to them. So they would say the whole time, the Earth did all the moving, so they're the ones that should age more slowly. We say the exact opposite, and both are valid statements. Yet, if we do the experiment, the one that traveled to Alpha Centauri and came back will actually age less. So how do you get around that paradox? That's what the minute physics will talk about. Okay, enjoy.